Hello everyone, welcome to Math 115, College Algebra. So in this section, we're gonna begin talking a little bit about trigonometry. So we're gonna start by explaining what angles are, how they're defined, how to convert between angles in degrees or in radians, like two different ways you can measure an angle. And then in later sections, we'll talk about trigonometry, so like right triangle trigonometry, and then the unit circle. Okay, and then finally at the very end, we'll jump to another chapter where we do some applications using trigonometry. But this section or this chapter is just to explain what an angle is. Okay, so in mathematics, there are some functions that repeat themselves in regular intervals. These are known as periodic functions. And one example is what's called a sine function. And let me just see if I can sketch this here. So a sine function looks like this. It's 0 at 0, and then it reaches a maximum of 1 and a minimum of -1, and it just keeps repeating itself forever. And it goes on both directions like this. Okay, so a sine function is an example of a periodic function. So this is a sine of x, where this is x, this is f of x. There's also another function. I mean, there's several trig functions, but another one that comes up all the time is the cosine function. Actually, I'll just draw it on the same graph. It's going to look like this. So it starts at 0, 1, and then it'll have a minimum right around there, maximum. It's going to kind of look like the reflection of this, or it's going to look like the sine function shifted, basically. So it's shifted by, it's hard to draw this exactly. So let's see. If this is where it should be 0, this is going to be the minimum, this is going to be 0, this will be the maximum, and so on. Okay, so again, it's just another function. So the red one is f of x equals cosine of x. It just oscillates, so the function repeats itself again and again and again. Okay, so let me begin by talking about angles and giving some definitions. And then later we'll talk more specifically about the sine, cosine function, and other trig functions. So first of all, let me start by defining a ray. A ray is a directed line segment. You can think of it as an arrow. An angle is the union of two rays. You're basically putting two rays together where they share the same endpoint. So is a union, I'll draw a picture in a second, of two rays sharing a common endpoint. Okay, so what we do is we fix an initial side, so we have like an initial ray, and then rotate to a terminal side, which is like our final ray. So we fix an initial side, then rotate to a terminal side. And the measure of the angle is basically the measure of the rotation, right? It's the amount of the rotation. So the measure of the angle is the amount of rotation. Okay, so let me draw some pictures here. Let's say I have a ray ED. Okay, so again, it's like an arrow, right? It starts at E, it passes through D, and it goes on forever. You can think of it as a directed line segment or an arrow. And then I have another ray, say EF. So they have the same endpoint, E, but this one goes through F. So notice that there's an angle formed, right, by those two rays. And there's several ways that you can name this angle. So the angle here, you can either name it as angle DEF. That symbol just represents, so this represents that's an angle. And DEF means I'm starting here, going, so the middle letter is always going to be the common endpoint. So it's like DEF, or you could name it angle FED. Or commonly we use these Greek letters like theta, phi, etc. You can just call it a particular name. Like I could just call this angle theta, right? That they're all equivalent, okay? But the key point here is the angle is formed by the ray ED and the ray EF. So angle is formed by the ray ED, I can denote it like that, and ray EF. Okay. What does it mean for an angle to be in standard position? Well, in standard position, I'm going to draw a coordinate system here. So I have my usual Cartesian coordinate system. In standard position, the initial side is directed along the positive x-axis. So, and this is really going to be 0 degrees. Straight up will be 90 degrees. This is 180, and then 270. This, by the way, is also 360, right, if we go all the way around. So the initial side is formed by a ray that goes from the origin along the positive x-axis. And then the final ray, the terminal side, is, say, right here. So the angle would be this angle right here. Let's say in this case it's like 30 degrees. So that would be an angle of 30 degrees in standard position. So again, the initial side is along the positive x-axis, and then you rotate until you get to the terminal side. Okay, let me write that down here. So initial ray is along positive x-axis. And then, because in this case I wanted to represent positive 30 degrees, The positive means to rotate counterclockwise. Okay, so I'll say plus means rotate counterclockwise. And if if you had a negative angle, that means rotate clockwise. Right, so again, in this case, I started along the positive x, right? That's my initial side. And because I wanted to represent positive 30 degrees, I rotated counterclockwise to the terminal side here. Okay, here's another example. Let's say we want to sketch an angle of negative 135 degrees in standard position. Okay, so again, this is 0, this is 90, this is 180, this is 270. However, if I go, so that's if I go counterclockwise, right? So 0, 90 degrees, 180, 270, 360, and so on. If I go clockwise, then this is still 0, but this now would be negative 90 degrees. This would be negative 180. This would be negative 270. And then if you go all the way around, this would be negative 360. Right? So it depends on whether you go clockwise or counterclockwise. So if we want to represent negative 135 degrees in standard position, I'm going to start with the initial side along the positive x-axis. And then because it's negative 135, I want to rotate clockwise. So this will give me 90, right? So right angle is 90 degrees. So that's 90 degrees. Then I need to go another 45, which is going to be right in the middle here. So it's going to be something like this. This would be the angle negative 135 degrees. Okay, so counterclockwise is positive, clockwise is negative. All right, and right now we're focused on degrees, but we could also measure angles in radians. So let's go over how to convert between radians and degrees. So sometimes we have to convert back and forth between those two units. Okay, so radians are just another measure of the angle. It's actually the more fundamental measure in some sense. It's what you would use if you're studying calculus or more advanced math. You would do things mostly in radians. So let me remind you what a radian is. So if I have, I'll explain this by drawing like part of a circle, like the wedge of a circle. Let's say I have a circle. I'll just draw part of it, where this distance I'll call the radius, right? Radius of the circle. This length right here, this is the arc length of the circle. So I'll call that S. And then this would be the angle, so angle theta. Now, if that angle is in radians, then by definition, what does that mean? It's simply the ratio of the arc length divided by the radius. Right? So the S is the arc length divided by the radius. And those are both lengths, right? So if I measure, let's say I measure this in meters, right? Or feet, it doesn't really matter. So I measure this, say, in meters, and I measure the R in meters. That ratio defines this angle in radians. Okay? So ultimately, because it's like, say, meters over meters or feet over feet, the units cancel. This is really a unitless measure here, the angle when it's in radians. We often we often write rad just to remind ourselves that it's in radians, right? Instead of putting a degree symbol. But it's really unitless, has no units, right? Because it's a ratio of a length to a length. All right, so how does that relate to degrees? Well, think about a full rotation, right? So if I draw a full circle, what is my arc length if I have a full circle? So the radius is still r, right? But if I go all the way around, if I have a full rotation, that's basically the circumference of a circle, right? So the arc length, if it's a full rotation, is equal to the circumference, which is this length all the way around, right? The circle. And if you remember, the circumference of a circle is given as, you can either write it as pi times the diameter, but the diameter is the same as twice the radius. So usually people write it as 2 pi r. So 2 times pi times the radius. That would be the length of the circumference. So in this case, if I want the angle that goes all the way around, theta, it's equal to the arc length divided by the radius. But the arc length in this case is the circumference, right? Because I'm going all the way around. I want this arc length, which is the same as the circumference if I go all the way around. So this is equal to 2 pi r divided by r. The r's cancel. So it must be, when I go all the way around, that the angle is equal to 2 pi radians. Okay? We also know that going all the way around is 360 degrees. So now we have, basically we have a relationship that we can form a unit conversion factor from. We know that 360 degrees is equal to 2 pi radians. Usually what people do is they divide that by 2, right, both sides by 2. So they use the conversion factor that 180 degrees is equal to pi radians. Okay, so again, to convert, and we'll do some examples in a second, you want to use as a unit conversion factor. So depending on whether I want to convert from degrees to radians or radians to degrees, I'm either going to multiply by 180 degrees over pi radians or pi radians over 180 degrees. Okay, if I want to go from radians to degrees, I would multiply by this unit conversion factor. If I want to convert from degrees to radians, I'd multiply by this unit conversion factor. There's also other ways you could do this. You could also form ratios. You could form like a proportion. So there's many, many different ways of doing this. I like to use unit conversion factors when I convert from radians to degrees. Okay, there's a few that you should just be familiar with, though. Again, we'll do some examples in a second on converting, but let me just show you this this diagram and a few of these that we should be familiar with. So this is a unit circle. And you're giving a lot of information here. In fact, you're giving the values for the cosine and sine of these particular angles. But the thing I want you to focus on is in the first quadrant here. These angles that are both in degrees and radians, you should know those corresponding values. So let me make a little table here. So we're more familiar with degrees, right? So I'll do degrees first and then radians. Okay, so first of all, 0 degrees is the same as 0 radians, right? And that's denoted here in the table. 0 degrees is 0 radians. 30 degrees, and we'll see how to get this, how to convert this, is equal to pi over 6 radians. 45 degrees is equal to pi over 4 radians. And you can approximate these, right, as decimal values. Remember, pi is around 3.14. So 3.14 divided by 6, a little more than a half, and so on and so forth. Another one you should know is 60 degrees. That is pi over 3 radians. And then 90 degrees is pi over 2 radians. Okay, and maybe we already know this one, I guess. 180, because this is the conversion, is pi radians. Right, so if I rotate by 180 degrees from here all the way to here, that's 180 degrees. It's also the same as pi radians, and you can see that here. Okay, but definitely I would know these in the first quadrant. Okay, the angle in both degrees and the corresponding angle in radians. All right. Now, let's go back and figure out how to actually do these conversions. Okay, so another way of doing this is you could set up a ratio, but I'd rather do it using unit conversion factors. But let me just mention this just in case you may have heard of this before. You could set up a ratio where you could say the degree value that you have or that you're looking for over 180 degrees has to equal the radian value over pi. So if you know the angle in radians, you can plug it in here and solve for the angle in degrees. Or if you know the angle in degrees, you plug it in here and you could solve for the angle in radians. Okay, so it's a proportion, right? But I think an easier way to do this is to use a unit conversion factor. So I'll say, or use unit conversion factor. And we just saw those, right? So if I want to convert from radians to degrees, so from radians to degrees, I want radians to cancel and degrees to survive. So I want to multiply the angle in radians by 180 degrees over pi radians. Okay, and if I want to convert the other way, I need to flip that, right? So to convert from degrees to radians, now I want to multiply by pi over 180. Why? Because now I want degrees to cancel and radians to survive, okay? So you'll see that in a second when I do the examples here. So let's start by converting radians to degrees. So this first example, I'm starting with pi over 6 radians. Now, I want my answer to be in degrees, right? So I need to multiply by a unit conversion factor such that the radians will cancel and I end up with degrees in my answer. So should I multiply by 180 degrees over pi radians or by pi radians over 180 degrees? I need to multiply by one of these unit conversion factors. And I want to actually use this one. Why? Because, I want radians to cancel and degrees to remain in the numerator. So if I multiply by this, you can treat units almost like numbers, right? Radians over radians will cancel, and I'm going to end up with degrees in the answer here. And then we just have to multiply this out, right? So I basically have pi over 6 times 180 over pi. The pi's cancel, and then 180 over 6, right? 6 goes into 6 once, 6 goes into 180, 30 times. So this is going to equal 30 degrees. So pi over 6 is the same as 30 degrees. Okay, what about pi over 9? So I'm going to start with pi over 9 radians. multiply by a unit conversion factor. I want my answer to be in degrees. So again, I better use the unit conversion factor where degrees are in the numerator, because I want that to remain, and then the radians are in denominator, so I'll multiply by 180 over pi. So now the radians will cancel, and then if you work this out, so pi over 9 times 180 over pi. Again, the pi's cancel. 9 goes into 9 once. 9 goes into 180 20 times. So this is the same as 20 degrees. Okay, so pi over 9 radians is equal to 20 degrees. Okay, what about negative 3/4 pi? Well, same thing, right? So I'm starting with negative 3/4 pi radians. I want to end up with degrees, so I better multiply by 180 degrees over pi radians. Radians cancels, so I have negative 3 pi over 4 times 180 over pi. Pi's cancel. I guess, let's see, 4 goes into 180 45 times, I think. Yeah, 45 times. And then negative 3 times 45 is negative 135 degrees. Over 1, so it's just negative 135. Okay, and then one more. Let's say we have 5 pi over 11 radians. We want to convert to degrees. So again, I multiply by 180 degrees over pi radians. Radians cancels. So I have 5/11 pi times 180 over pi. Pi's cancel. This one, let's see, 11 doesn't go into 180, so I guess let me just multiply numerators. That'll be 900 over, and denominator's 11. So it looks like it's 911 degrees would be the answer. Or if you approximate this with a calculator, it's around 81.8 degrees. Okay, so 5 pi over 11 radians is around 81.8 degrees. Okay, what about going the other way? So what if I start with degrees and I want to convert to radians? Same sort of thing, except now I have to flip the unit conversion factor. Right, so if I start with 15 degrees, I want to multiply by unit conversion factor, end up with radians. Now I need to use pi radians over 180 degrees because I want degrees to cancel. Okay, and if you work this out, right, this will be 15 over 1 times pi over 180. And let's see, I guess, does 15 go into 180? Yeah, I think it goes in 12 times. We could factor this, right? If I do, let's go back to our prime factorization to make sure. So this is 3 times 5, and then 180 is 2 times 90, 2 times 45, 3 times 15, 3 times 5. Right? So this will be equal to 3 times 5 times pi over 2 times 2 times 3 times 3 times 5. Yeah, so 15 does go into it, right? So this is going to be pi over 12 radians. Okay, and we can do that this for the other angles as well. So 300 degrees. If I want to convert to radians, I multiply by pi radians over 180 degrees. Right, that'll be my answer in radians. So what is 300 times pi over 180? You can think of this as over 1. Well, definitely 60 goes into both of these, right? 60 will go into 180 3 times, and 60 goes into 300 5 times. So I guess this is going to be 5/3 pi radians, or 5 pi over 3, same thing, 5/3 pi radians. Okay, and then finally the last one. was 126. And I want to convert that to radians. So again, I'll multiply by pi radians over 180 degrees. And then if we simplify that, this is 126 times pi over 180. Okay, here again, I'm going to find the prime factorization because I don't know this, can't do this in my head. This is going to be 2 times 63, right? Then 3 times 21, and then 3 times 7, and then 180 is 2 times 90, 2 times 45, 3 times 15, 3 times 5. So this is going to be 2 times 3 times 3 times 7 times pi over 2 times 2 times 3 times 3 times 5. So I guess the 2's cancel, the 3's cancel, and it looks like I have 7 pi in the numerator and then 10 in the denominator. So it looks like it's like 7/10 pi radians. So 126 degrees turns out to be 7/10 pi radians. Okay, so really that's all you're doing for converting from degrees to radians or radians to degrees. You're just multiplying by the correct unit conversion factor, either pi radians over 180 degrees or 180 degrees over pi radians. Okay, one last topic here. So often we're going to prefer to work with angles that are between 0 and 360 degrees, or correspondingly, if you're in radians, between 0 and 2 pi radians. So it turns out that any angle that we have is going to be coterminal with an angle in that range from 0 to 360 or 0 to 2 pi. So, for example, if I have 800 degrees, all right, what does that mean? So first of all, here, I'm going to draw a picture here. So I have my coordinate system. Since it's positive 800, that means I'm going to start at the positive x-axis and rotate counterclockwise, right? It's positive. And to get to 800, I need to go around once, that would be 360, around another time, that would be 720, and then another 80 degrees. So something, let me see if I can draw that better. Something like this. So I start right at 0 and I rotate twice around plus another 80 degrees. And that angle would be the 800 degrees. Okay? But what we're saying is this angle is coterminal. In other words, there's another angle that I can measure from the positive x-axis, from that initial side, such that it's just in the range from 0 to 360. And what is that angle? Well, that angle is right here, which was the 80 degrees. Right? So how do you find that in general? Because we kind of just thought about it. If I rotate around once, it was 360. Another 360 is 720, and I need another 80, right? So that coterminal angle is 80 degrees here. But the way to figure this out is if I start with 800, I can basically just subtract 360 degrees until I get in the range between 0 and 360. Okay? So the way you can do this is subtract 360 degrees until you get a number between 0 and 360. Right? Because I want to get in the range between 0 and 360. That's the range we prefer to be in. So if I do 800 minus 360, that will give me 440. Okay, I'm still not in that range, the correct range. So I start with 440, I subtract another 360, and I'm gonna get 80. And that is the answer, right? Again, the picture is the original angle of 800 degrees, which is here, is the same as an angle if I just went 80 degrees, right? So that's what they mean by coterminal. Like this terminal side is going to be the same for 80 degrees and 800 degrees. Okay, let's do a few more of these. Let's say I have my original angle is negative 123. So that means I want to measure this clockwise. So this would be 90 degrees, right? Then I need to go, another 33. So I'm in this third quadrant here. Something like this. So this angle would be negative 123 degrees. But I want an angle that's between 0 and 360. So really, I want this angle. Right? Because 0 and 360 means measure counterclockwise, where I'm going to end up with the same terminal side. So this angle, negative 123 degrees, what is it equivalent to if I measure this angle? Right? The one that's between 0 and 360. And the way to figure out that is you could just add, you could think about this, right? It turns out if you just add 360 until you get a number between 0 and 360, that will work. So if I add 360 degrees until you get a number between what we want, which is 0 and 360 degrees. So in this case, I can just do this once, right? If I add, think about why this works. If I start here at negative 123 and I add 360, that means I'm adding a counterclockwise angle of 360 to get back to here. So if I do that, I'm going to get the angle I want, which is 237 degrees. So it's saying this angle in the blue here is 237. And that's what I want because I wanted an angle between 0 and 360. Okay? We could do the same thing with radians too, right? So if my original angle in radians was 15/4 pi. Now, to figure this out, remember that a full rotation is 2 pi radians. Or because I'm dealing with fourths here, it's the same as 8 pi over 4, right, radians. So to get to 15/4 pi, I need to rotate, this would be 2 pi, right, or 8/4 pi. And if I do another 7/4 pi, so that's going to be to here, that will give me the angle I want. So I start here, again, always positive x-axis, and I want this angle right there. Okay, so that would be the angle 15 pi over 4. But if I want the coterminal side where the angle is between 0 and 2 pi, I really want this angle, just from here to here, right? I'm drawing it in blue now. So how do I do that? Well, I could just subtract 2 pi radians until you get a number between 0 and 2 pi. Okay, so if I start with 15 pi over 4, I want to subtract 2 pi, but remember that's the same thing. Let's write these so they have the same denominator, right? The lowest common denominator, which is 4. So this is 2 pi is the same as a fourths pi. And if you work that out, that's going to be 7 fourths pi. And that number is between 0 and 2 pi, right? It's between 0 and 8 fourths pi. So this blue angle right here is the coterminal angle, and it's the one we want, the 7 fourths pi. Okay? So often we might be giving some angle, and we want to put it in the range 0 to 360, or equivalently 0 to 2 pi, right? 0 to 360 degrees, or 0 to 2 pi radians. So that's what you do. You're basically either going to subtract 360 or add 360 until you get a number in the range that you want. And if it's in radians, you're either going to subtract 2 pi or add 2 pi until you get the angle in the range that you want, between 0 and 2 pi. All right, next time we're going to start talking about some of the trigonometric functions, and we're going to focus on right triangle trigonometry to begin with. And then we'll talk about trig functions of any angle in the section after that. Great, thanks.